hot classmate. Today we're delighted to have Professor Yu Bin Chen from Mechanical Engineering to share with us his insight on the nanotechnology. He will provide the introduction for us today. Let's give him a warm welcome for this rainy day. Thank you.
Thanks, everyone, and I'm glad that to see all friends from a lot of countries. I guess from Africa, America. Anyone from America? Great. Okay. Asia, most of you, right? And how about Europe? Wow, great, great. And Australia? Okay. Do we have? Oh, okay. I guess no one comes from the South Pole, right? Okay, yeah. So this is the second time I attend Professor Xie's class. Actually, this slide was prepared last year, and I'm glad to give a pretty much similar talk this year, and to have a kind of a brief introduction to nanotechnology, history, definition, methodology, applications, and the challenges. So basically, I will cover 5 categories within this talk. And if you have any questions regarding to my presentation, just raise your hand. And since I have about 90 minutes, so I should have plenty of time to cover the whole contents. So first, I will start with the outline today. Basically, we'll cover the 5 categories I just mentioned, and I will start from the history. And the history, I will divide it into the China and other countries because we have a long history. So previously, our philosopher, one of them, Gong Sun Long, mentioned that basically he said that 1 feet of wood, if you chop half a day, basically, you need an infinitely long time to chop it till the end. Because every day you got half out, but you still have half remain. So that means that basically you will have forever to have the wood chopper into, let's say, to 0. But this is not true in reality, as most of you know. That physics tells us that if you chop the wood every day half, then at the end, what do you get? It's like an atom, molecule. It's not wood anymore. Basically, the property changes down to that tiny scale. You still get something, but the property of that thing is different from the bulk wood. So here is the continuum assumption that a medium is indefinitely, I'm not familiar with this one, is indefinitely divisible without changing its physical nature. That's a continuum assumption. And what I mean by physical nature, such as density, color, electrical conductance, and so on. This assumption works for most scales, but it breaks down to the nanoscale. So that's why nanotechnology or nanoscience is important. Not a microscale, not a millimeter scale, it's nanoscale. Because the continuum assumption breaks down. And then let's give an example of the continuum assumption. So basically, how we define the density. You may not be familiar with the density, but basically if you go to the shopping mall or like say convenience store, you buy something, it will tell you CP value, right? How much you need to pay for, let's say, 100 milligram. And that's the same thing for the density. How we define the density? The dou. It's basically you define a volume or circle a volume you measure the weight. At least you measure some mass. Divided by the volume, you will get density. So let's take a bag of air, for example. You have a bag. Inside, you have air molecules. And then you measure the weight of the bag. Divided by the volume, you get the density of air inside. This kind of idea for the density works perfectly if your bag is large enough. You have a larger bag, small bag, fine. But if the bag or the volume continues to shrink, then the problem happens. The continuum assumption breaks down because you know that air is composed of a lot of molecules. When the volume keeps shrinking down to the nanoscale size, basically you need to quantize how many molecules inside. And the density will not be a constant anymore. Sometimes you have 5 molecules inside. But if you shrink a little, then you only have 4 molecules. So the change of the density, or actually the mass, is quite large. Even your volume changes a little. So the density is not a constant anymore when it goes down to the nanoscale. So that's why we need to consider this kind of continuum assumption breaks down when the nanoscale. And how about the foreigners? I mean, the Americans, I would say. This guy, Richard Feynman, we consider him as a pioneer of nanoscience and nanotechnology. The reason is that when he gave a lecture in 1959, he visioned the nanoscience or nanotechnology. During his talk, basically you can find the whole content of his talk within this website. But during his talk, several points were made by him. One of the points is that why cannot we write the entire 24 volumes of this book on the head of a pin? How is he going to do it? He said, okay, suppose we have a machine. We can fabricate parts. And those parts could assemble another machine which is smaller than the previous one. And that machine can fabricate parts composed another machine which is smaller than previous two. If it continues to shrink the size, basically you will have a tool can fabricate or can write with a very, very tiny scale. So he visioned this kind of nanoscience and nanotechnology can do things within a very, very small scale. And what he means the scale is nanoscale. And the history, I conclude here. Basically, Richard Feynman gave the talk in 1959. And after that, basically, the nanotechnology has formally initiated. For example, in 1974, the Japanese guy, Takuchi, used the term nanotechnology in paper. 1981, the first technical paper and the scanning tunneling microscope invented. And here are some other important progresses, like first company founded. And what I want to say is that in 2000, President Clinton announces the U.S. National Nanotechnology Initiative. It is considered a formal step of government to support the nanoscience and the nanotechnology. So it boosts the progress of the nanoscience and nanotechnology. And 2011, we have some other progresses here. So if you are interested, you can look into more detail about the development history of nanotechnology. But what I want to emphasize here is that it is a global trend to put emphasis, fundings, resources on the nanoscience and the nanotechnology. Then let's go to the definition. What is a nanometer and what is the nanotechnology? Let's start with the nanometer. Nanometer, in Chinese, we call it a 奈米. So my mother sometimes will ask me, she asked me several times, what is nanometer? Can those rice be eaten? You know, mi is rice. So 奈米, she considers as a kind of a food, the rice. So she wants to know the taste of that. And how can she feel it? She wants to measure or kind of see it. I said, well, nanometer is a dimension. Okay? Actually, it's called nanometry. And the American spelling is nanometer. It combines two words. The prefix is a nano. What is nano? 10 power minus 9. Meter, everybody knows that. So nanometer means that 10 power minus 9 meter. It's quite a tiny scale. And it is often expressed or used to express dimension on the atomic scale diameter of helium, for example. It's about 0.1 nanometer, or we say 1 angstrom. It's about 10 power minus 10 meter. So basically, I tell my mother, you cannot see it, you cannot eat it, and you don't want to eat it. Because when you eat them, you feel nothing. I mean, the food with the nanoscale scale, you can imagine how much you need to get your stomach full. So, and if you use a comparison, let's say 1 meter and 1 nanometer, it's just like the diameter of our Earth compared to this kind of glass balls, the scale. So you can know that it is quite small. And let's say if we want to put our focus from the millimeter down to the nanometer and compare to the electromagnetic wave, or we can say light. Here is the graph to give you another idea from another aspect to see what is a nanometer. The left-hand side tells you the wavelength, the scale. The middle line tells you the dimension. The right-hand side tells you the characteristic dimension. For example, let's start from the longest one. Which side? The radial wave, 10 centimeter. It corresponds to semiconductor wafers. And down to 1 centimeter, still microwave range. And now you got the 1 millimeter, 100 micrometer, down to the nanometer. And you have the far infrared, mid infrared, near infrared, and visible. So if we put our focus on a nanometer, basically we are talking about wavelengths about ultraviolet, and even deep ultraviolet, and X-ray, because here is the nanometer scale. And what's the dimension we usually need to use nanometer to measure? Like here, a nanoprobe, nanorod started from nano. So everything starts from nano, basically is a nano size. And compared to that, smaller you have molecules. So molecules depends on what kind of a material that you are talking about. But basically the size is around nanometer to tenths of a nanometer, something like that. And a little thicker is like integrated circuits. And sometimes you have coatings like the coating of your glasses. The thickness basically is a nanometer scale. And if we are talking about another smaller scale, 1 angstrom or 0.1 nanometer, we have a lattice constant or atoms. So basically, this picture gives you that when you're talking about nanometer, basically you are talking something maybe related to here. And if you are talking about light, the wavelength measured with the nanometer, you are talking about deep UV, something like that. And President Clinton initiated the National Nanotechnology Initiative, NNI. And he or that NNI defines the nanotechnology. It says that research and technology developed at the atomic, molecular, or macromolecular levels in the length scale approximately 1 to 100 nanometer range to provide a fundamental understanding of phenomena and materials at the nanoscale and to create and use structures, devices, and systems that have novel properties and functions because of their small and intermediate size. We call it nanoscience or nanotechnology. And what I want to emphasize are put in red color. We are talking about atomic, molecular, and macromolecular levels. And then the other thing I want to emphasize is that basically you are talking about novel properties or functions because of tiny scale. So if you remember at the beginning of this class, I emphasized what? The continuum assumption. Those novelty, because of a small scale, is what? Is the continuum assumption breaks down. So the material itself no more shows its property anymore. It shows something new. That's because continuum assumption breaks down. So here gives you the idea. Because of its tiny sizes. The second paragraph gives you the nanotechnology research and development, the contents. What does it contain? First thing, manipulation. Okay? And within these larger assemblies, basically you can control the composition of their structures and remain a nanometer scale. In some particular cases, the critical length scale for novel properties and phenomena may be under 1 nanometer or a little beyond the 100 nanometer. But basically, we are talking about using nanotechnology to manipulate material properties and to construct something, even build up devices that we can use. Here are some examples about the macroscopic formulation that breaks down or changes down to a nanoscale. And since most of you do not have a physics or engineering background, those words may be unfamiliar to you, but you just try to understand as much as possible because those are just a kind of an idea. Okay? For example, the temperature. We know what a temperature is. For example, you have a fever, you put a thermometer on your head and measure the temperature. But at the nanoscale, the temperature cannot be defined. Why? Let's imagine. We are talking about temperature. What do? You measure it. Basically, you measure what? You have something in contact with your forehead and to measure how hot it is, right? And those hot is just like the molecules are dancing, like wave dancing. When you are cheering and you are so excited, you just jump out and then sit down, jump out and sit down. The more excited, those molecules jump out and down. But down to the nanoscale, you don't have enough molecules to dance. So what do you measure? You measure nothing. Either you touch one molecule or you touch nothing. So the temperature cannot be defined at the nanoscale. Okay. Another thing is the thermal conductivity. The same thing. This is made of metals. So if you use if you put one end into fire, you will feel hot easily at the other end. But if this kind of thing is made of nanoscale, sorry, it cannot have the heat conduct so easily because you only have one pass. The molecules just in a line. So it's very hard for those hot temperature or excitation to move from one end to the other. The rest, I will just skip them because some of them may be unfamiliar to you. So if you are interested, we can talk about in details later. But basically, those properties will change at the nanoscale, or some of them may break down with. Even most of them work in macroscale, but you will break down in the nanoscale. Now we shift the focus to the methodology. So if we want to use the nanotechnology, the first thing is that you need to see. You want to know what's going to be fabricated. How does it look like? Does it look the same as you expected, as you designed? So we need tools to see things down to nanoscale. And the first tool, the first instrument I would like to introduce is the SEM, the Scanning Electron Microscopy. Here, the left side shows the principle. The right-hand side shows some results of that. One is the blood cell, the red blood cell. The other is the structures. And the left-hand side shows the principle. Basically, you have an electron gun at the top. And you hit it, generate an electron. And due to those kind of field generated by those magnets, the electrons will focus and then shoot out your sample. And then bounce back, and then reflects out, or I would say scattered. And those scattered electrons will be collected by the detectors. So it depends on the distribution of those scattering electrons. You know the profile of the samples. So what I do this time, last year I don't have this kind of thing. Now I use this kind of ping pong ball to show. If this is the flat surface, if you shoot the ping pong ball, what will it bounce? Where does it bounce? Just vertically, right? But if you shoot at, let's say you have a rough surface, so it will go to other directions. So it depends. If you shoot a large amount of ping pong balls, and you collect them. Okay, next time I will practice first. So you know how this profile looks like. If it is a flat disk, you will get most of them scattered in the right normal direction. But if you get a rough surface, like those blood cells, you will get them bounce to other directions. And use those scattered electrons. You kind of can have this kind of image to tell people that what's the sample look like. The second tool, transmission electron microscopy. Basically, the same principle. except now the sample is very thin. So the ping pong ball can penetrate. So what you get is not the surface profile. Basically, it shows how the transparency of the sample. So you take a cross-section, very thin, and you shoot those electrons. You can get the images. Depends on if the material is transparent or not. So that's the second tool that we can inspect the profile or get images of your sample at the nanoscale. So we still have an electron gun at the top, and then we control its direction with a lot of magnets and focus, and shoot down the sample, and you put the detector at the bottom. You receive those scattered electrons. That's how TEM, transmission electron microscopy, works. The third one, AFM, atomic force microscopy. This actually is quite intuitive. It measures the profile down to the nanoscale with probe. Even not to the nanoscale, you can measure the profile with probe. How? Use this pointer as an example. If you scan the desk, you touch it, nothing happens because it's smooth to the pen and it does not need to move. But when this pen hits something, it needs to raise so that it can keep scanning. The distance it raises tells you the profile or the thickness of this box. So very simple. But when it goes to the nanoscale, it's not so sensitive. So the pen, even it moves, let's say 10 nanometer, 30 nanometer, you cannot see anything or feel anything because the movement itself is quite tiny. So we need some kind of mechanism to magnify it. So what do? We use the tip with a sharp end, but this kind of tip is at the end of the cantilever. The cantilever is like what? Another toy. This is my name card box, but I use it as a toy to demonstrate the principle of this cantilever. The backside of my name card, this box is like a mirror. The same thing for this tip. So if I use this laser point to shoot down this, no, I will just skip it right now. If I use this pointer to shoot down this box, so you will see one point. But if I tilt the box a little, you will see the signal actually move a lot compared to the distance or the change of this mirror. So it's just like an optical lever, magnify the position change of this tip. So if I put the tip at one end, even it moves a little, quite tiny, but the signal will change a lot. So I can magnify the position and to reversely to tell the profile of this nanoscale box. So that's the principle of AFM. So the AFM principle actually is quite easy. It combines the probe technology and the optical lever. This combination of two technologies actually give the inventor a Nobel Prize. And a lot of companies fabricate AFM. So if you are smart enough, then you can make a lot of money. Actually, it's not quite difficult if I tell you, right? But if you can imagine this kind of thing, let's say maybe the AFM, when it starts, let's see. AFM, 1986. So if you know what I just said before 1986, congratulations, you already made a huge amount of money and a Nobel Prize. Not difficult, right? A liver and what? And a pro. That's it. So this is AFM. So use this AFM, basically you did not or you cannot see the profile, but use this kind of change of the light patterns, you can tell what's the profile down to the nanoscale easily. The fourth one, focused ion beam microscopy. The left-hand side tells you the cross-section view of the instrument, and the right-hand side tells you the pin to emit the ions. So if you don't want to see the words, then I just use a kind of a toys to tell you the same thing as I just did for the SEM. Let's say you still remember how SEM works. Ping pong ball, right? Ping pong ball shoot on the desk, and then you get the response. And then the scattering patterns tells you that how the profile look like. But for the FIB, focused ion beam microscopy, not ping pong ball. Golf ball. The size is different, the mass is different, but the principle is the same. So it uses ions instead of electrons to shoot on the sample, and use the scattered ions to tell the profile of this sample. And then you can see the profile down to nanoscale. And I guess most of you will have a question right away. Then why bother? Since the electrons works pretty much well, then why use ions? Yes. For ions, it has some advantage, or at least some difference from an SEM. Let's just imagine, if I shoot ping pong ball on your face, and use a golf ball to shoot on your face, what's the difference? Yes, Professor Scher right away tell you, it hurts if you shoot a golf ball, right? Much hurt, right? Ping pong ball is maybe okay, right? So the same thing. If you use ions, because its mass is much larger than electrons, so what you can do is basically you can shape the profile. So it's like a milling machine. You kind of manipulate the profile with those ions. Electrons, not really. It just shoot on and then scatter. The profile remains. So the focused ion beam actually not only provides you the scattering image, but also can be used, actually most of the time they are used to kind of manipulating the profile down to nanoscale. So it's a machine tool. Precisely speaking, it's a milling tool. So you can kind of dig a hole or kind of dig trenches with those focused ion beam, and you can still see the image. So for engineers or for researchers, what we do is that we combine the focused ion beam and the SEM together with one instrument. So we basically manipulate the profile and then we inspect with ACM. We manipulate the profile with the FID and then we see the image with the SEM. And that's what we usually do. But some people do see profile with a focus ion beam as well. So basically, it not only serves as an inspection tool, but also a fabrication tool for FIB, because it uses a ball which is about the same size or a little larger, but the mass is quite large. So it can shape the profile. So if I shoot a disc off, strongly, the disc will be knock out some part. So that's how FIB works. And if you are interested in details, then you can see the slides in more detail or look up in the textbook. But what I want to cover is that FIB, the principle is basically the same as a SEM, except it uses other ions instead of electrons. And usually gallium ions are used. Okay, and since I already mentioned about the fabrication down to the nanoscale, then two types of fabrication skills were widely used. They are in the opposite direction, I would like to say. The first one is called bottom-up. So if you see the right figure, bottom-up start from atoms. Like a chemistry, it manipulates atoms, get together, shape up, and then build up into clusters. Clusters composed of nanostructures. That's called bottom-up. Those kind of things, or these kind of techniques, actually takes quite a lot of time, but it controls the shape pretty well. It is good for researchers. The other way, for fabrication, top-down. Top-down starts from a bulk material. Then you get rid of those you don't want. Use of FIB and other things, etching, something like that. So you have a bulk material, and then get it into a powder, and then divide it into or split, and get rid of most of them. Then you get the nanostructures. These kind of fabrication techniques are good for mass production. So if you want to fabricate nanostructures or something about nanotechnology, basically, if you want to make money, usually people go top-down. But if you are going to do the researchers, you want to get your sample perfect, then you go bottom-up. And the detail and fabrication techniques that I want to cover in this class. But if you are interested, since I'm a mechanical engineer, you can discuss with me after class. So let's move to the fourth topic of this lecture, applications. About nanotechnology and nanoscience. And before I want to cover, I would say I have plenty of applications used nanotechnology. But during this class, or after class, most of students will remember one thing only: chocolate. I don't know why. Maybe because chocolate is your favorite. I don't know. Even Professor Xie remember chocolate only. Okay, so why chocolate is related to nanotechnology or nanoscience? Basically, the chocolate. Here is a table. The chocolate itself is a crystal, right? You buy it from a supermarket and then you chew it. You will feel it's cracked easily and then tastes good. Why? Because it is a many type V that you are chewing. So this is the characteristic of this type V, or the fifth type of the chocolate. But if you melt it, let's say you put it in a pocket, or during this summertime, you have a chocolate in your bag. Later on, you find it melt. And then you say, okay, it melt. I just put it in the refrigerator. It will frozen back. No. If you taste it again, you will find that it tastes differently. Why? Because nanoscience plays a role inside. Those molecules will not form type V anymore. It goes to type 4 or type 6. I think it's type 6. The self-assembly takes time and stable and very well temperature control. So for those companies, vendors, fabricate chocolate, it control the temperature around this temperature a little lower, so that those molecules, chocolate molecules, will shape up in the right form, so that the customers enjoy chewing chocolate. But if you don't know how it self-assembly, you just frozen in the refrigerator, the temperature cools down right away. The type 5 cannot form uniform. So most of them are not type 4. Then you will think, oh, how come the chocolate changed? No, the same chocolate, except their assembly shape or form is not the same. So that you don't like the chocolate melt and then frozen back. Smartphone. Smartphone is another example of nanoscience and nanotechnology. Even you do not know what is nanoscience or nanotechnology, but you can use a smartphone easily and you pretty much enjoy it. What is a smartphone? Basically, it composes the functions of camera, recorder, Game Boy, and radio, even a lot of things, right? And how these kind of functions can be combined into one small box. It's because that a lot of the chips, the multi-chips, shrink its size. And to fabricate those chips, those wires, you need nanoscience and nanotechnology. For example, the line width between two metal wires is about the 10th nanometer in those chips. So that your smartphone basically can function like a combination of a previously bunch of instruments together. Previously, if you want to have a radio, or you will have a large box. A camera, even nowadays, you need to have a camera like such big. And the tape recorder, the same thing. Previously, a phone is larger than cell phone now, the smartphone now. The size downgrade should thanks to the nanotechnology. You can have a lot of chips, wires that have a very, very small scale that can be shrink into this tiny box to realize the smartphone. Cosmetics. For most of you are, young women should be pretty much enjoying cosmetics, and you saw a lot of advertisement that talking about nanotechnology employed in cosmetics. And here I give you two examples that cosmetics use nanoparticles. The first one is what? The titanium dioxide, TiO2, or zinc oxide. They are used for what? Basically, they kind of prevent the ultraviolet. So it blocks ultraviolet to protect your skin. The other one is the solid lipid nanoparticles, SLN, and the nanostructure lipid carriers. It enhances the skin hydration, so that it keeps your skin moisture. Okay, those two types of nanotechnology products have been widely employed in cosmetics, and they claim that either they can prevent the ultraviolet, not hurt your skin, or keep your skin moisture, just like water. You know, beautiful woman usually like that. Okay, so those are products employed in cosmetics that are related to nanotechnology. Morpho is kind of animals that use nanotechnology, and we humans employ this kind of nanotechnology in our daily life. It can be used as a fabrics, dye-free pens, and anti-counterfeit in, let's say, your paper bill. Why? Because its wings has colors, and those colors are not generated by the morpho itself. It diffracts the light shoot on its wings. So, depends on the light and the angle, it will show different color and very attractive. So even clothes use this kind of nanotechnology. Some people like to wear this kind of clothes because it shines. And then if you have a different perspective or different view angle, you will see different color. Quite attractive. So this is another nanotechnology that because tiny or nanostructures can diffract light. And those diffracted light will tell you eyes that are different color. So this kind of thing is another example of a nanostructures can be used. So like a fabrics, dye-free pens, and anti-counter relief technology used in currency. Lotus effect. So not only color can be manipulated by those tiny structures, the nanostructures. The Lotus effect is another well-known effect brought by those tiny structures. The lotus leaf have nanostructures on top. Those nanostructures actually has two types. One is larger. The other one is quite small. And they are on top of the first one. So with those two types nanostructures together, the lotus leaf can prevent the water staying on its leaf. That's natural. How is it going to be used? For products, let's say solar cell, for example. What do we do with the solar cell? Solar cell is something you collect the sunlight on top of your roof, right? And basically, the more light you accept, you get more energy. Above it, you have a transparent glass to prevent the break and water and something, right? But then, those transparent film or glass will be what? Will be dirty by dust, by pollen, by particles. So how are we going to prevent it or clean it? You don't want to hire or recruit somebody to clean your solar cell on your top, on your roof every day, right? So how are you going to do it? You use the Lotus effect. You made nanostructures on top of those transparent film or glasses. So those rains, when it rains, will wash away the dirt on top of your glass or your film. so that the solar cell always have a transparent and a clean film to absorb the solar energy without blocking or being get dirty by those particles and the dirt. So this is another example of nanotechnology. You use those nanostructures to prevent the dirt accumulate on top of your solar cells. I guess I kind of end up today's class a little early because I only have another slide. But I would say this topic, the fifth topic, is the last one, but not the least one. It's about challenges, risk, and ethics. So previous four, basically I give you a rough idea, what is nanoscience, what is nanotechnology, and how are they going to benefit our daily life. But in the fifth talk, I will give you another viewpoint. I list the 5 points that we need to think deeply before rushing into nanotechnology and their products. The first one, can we monitor the exposure of nanoscale engineered particles to humans in the air or within water? Basically, as I claim, those nanostructures are so small that you cannot feel it. But when it accumulates in your body or on your face, you don't know what's going on. And the effect will be sensed maybe after 20 years accumulation, even more. So how can you monitor it is the first challenge. You need to know how much it is accumulated. For example, you are a cosmetics lover and you put the nanoparticles every day on your face. Are you sure they are washed out before you sleep? If not, what will happen the other day? What will happen 10 years later if they keep accumulating on top of your face? Okay? The second point I want to mention or emphasize is that can we develop and validate methods to evaluate the toxicity engineered nanomaterials? Nanostructures or nanoscale materials do bring benefits to our daily lives, but they may bring the toxicity or their byproducts during their fabrication may bring toxicity. We do not know. Actually, we have no idea because they are too small and they cannot be seen or sensed unless you put them under the SCM or AFM or whatever. So you never know. And we need to have something, or at least someone, to work on the developing or validate their toxicity before we use it, right? Those cosmetics vendors will not tell you how much hurt or how toxic their byproduct is, right? They just tell you, okay, it's good for your looking currently. I'm not sure after 10 years though. But currently, it makes you feel good, look good. The third one is that we need to constructing the models or to predicting the potential impact of those nanomaterials. Just like weather prediction. You need to predict those nanoparticles. What if we continuously use it? Or even we enlarge the production of that? What's going on? What will the world be? And then remember, just like the food chain, those nanoparticles may somehow, someday accumulate in your body. So we do not know. You need to construct a model of that. The fourth one, is related to education. Most people know the challenge, the benefits, the future, or potentials of nanotechnology, but they are not aware of those cons. They know pros, may not know cons. And those cons basically are not emphasized compared to pros. But for us, like an educator or faculty in universities, or even later on, for you, will become a boss or supervisor in a company. You need to tell people, or somehow you may become a father or parent, like mother of a child. You need to educate your children. Nanotechnology is not perfectly thing or perfect technology. It has some cons, but you need to balance it. It do have a pros, and then you need to explain both pros and cons to your children, your supervisee, your students, so that they know what they choose. They are not rushed for anything. The fifth one is that we need to define areas applicable to nanotechnology with regulations and laws. That's something government or legislator or lawmakers should be put in mind. You need to make laws so that the vendors follow. Commercial ads won't emphasize or overemphasize their functions and neglecting their drawbacks. So you needed to, otherwise you will have our society into another dangerous situation. So we don't want to emphasize the functions of nanotechnology, and these kind of things should be prohibited. So that's the fifth one I would like to mention about the challenges and risks and the ethics that are related to nanotechnology. And then there are others more you can imagine. So I pretty much will end up today's talk right here. But I want to say is that the 5 topics today will give you a rough picture of nanotechnology and nanoscience. Even my research is related to the nanotechnology, but I still put quite caution on my research and to warn my students that you are dealing with nanoparticles, nanostructures. You need to know that's something that you cannot see, but that's something you can may have an influence or long-term influence on your mind, on your body, and everything. So pretty much I finished today's talk. I now be ready for taking any questions. Okay, wow, sorry. Yes?
I have a question about fabrication of nanoscale structures.
Yes.
There are 2 types of fabrication. One is the bottom-up, and the other is the top-down.
Yeah.
I just want to ask, which one is more difficult, practically?
Which one is more difficult in practice? As I claim that if you want to have a high accuracy and high precision, basically the only choice or the better choice will be the bottom up. And if you want to do the mass production with sufficient tolerance, you will go top down. In case of challenges or difficulty, I would say that compare these two, the bottom up is more challenging. Yeah, basically you need to have generally researchers just focus on one sample at a time. So you need the time, patience, and the resources. So more challenging. So if you are a boss running a company, you will not go that way. Yes?
mentioned that the USA has a nanotechnology initiative, but
Yes.
does Taiwan also endorse nanotechnology and R&D?
Yes, we follow the steps of America. So basically, our National Science Council also support or initiate the national project of nanotechnology. And we funded several big projects with millions US dollars for that. Yes, we do follow the step of United States.
So what kind of focus do you have in Taiwan regarding the many different applications of nanotechnology?
If you want to say that, I would say for government or the National Science Council, basically it's a diversified focus. So it covers the nanomaterials, nanofabrications, and nanoscience, like a near field spectroscopy, something like that. But for companies or the current companies in Taiwan that employ the nanotechnology, I would say like a TSMC, they use it for semiconductor fabrication. And the nanotechnology benefits their production and profits because as I claim that it can shrink the size. And the TSMC basically got fabricated chips. So the more size you can shrink means a high density from the same unit area. So it brings much benefit for fabrication. So the semiconductor company, I would say, the most benefit from nanotechnology. Yes.
Can nanotechnology also be used to cure illnesses, for example, or to implement in the pharmaceutical industry?
Good point. Yeah, actually I deleted that slide. In reality, nanomaterials actually can be used for like bones, teeth, these human replacement of their body and their body parts. I would say. My English sometimes I may not use the right word, but the benefit of nanotechnology compared to the traditional ones is that the nanomaterial and the nanostructure, they can manipulate so that focus, the germs cannot be accumulated easily. And it's clean easily. Like a user ultraviolet, you can clean it very easily. So this kind of thing has been considered, employed for the human science and human health. Yeah. And the drugs also. But the drug, I would say, should be cautious because you are not sure what's going on when it accumulates a large amount of in your body. So that thing is developing, but currently I have no clear picture how are they going to use. But the cosmetics, that's for something for sure. Yes.
My question is right now, there's a huge population all over the world of people are doing a lot of research about nano processing and that kind of research. So what are the pros and cons of this nano food?
You mean nanofluid?
Nano
Nanofood.
yeah.
Okay. Nanofood, that's the idea that it's a little vague to me. I would say that the nanofood, to me, basically the food itself is not nano size for sure. But basically the components or inside ingredients may be nano size or kind of you can add something inside. Is that correct? Did I misunderstand your meaning of nanofood? What do you mean nanofood, I would say?
Because from the farmer,
Yes.
there's a lot of processing,
Right.
There's people using a lot of nanotechnology processing.
Okay.
What is the impact in that whole thing?
Okay.
From the farmer to the consumer.
Okay. Okay. Now, roughly I understand. The nanotechnology has been used in the food from the farmers up to the customers, and you want to know the impacts, right? And I would say that basically, the food related to food, people are more concerned about the gene technology rather than nanotechnology. You have to manipulate the genes like a corn. Usually, it can get eaten by worms easily, but nowadays you will get a sweet, large corn with some kind of manipulation in genes. So nanotechnology may be involved in gene technology, but people are challenging or concerned with more genetic manipulation rather than nanotechnology. And for the fabrication and the packaging of the food, the nanotechnology actually did not do much help. So I would say that unless you kind of link the gene technology with the nanotechnology, and basically they are different things. Because yes, gene is a very tiny scale, but that's another technology that I would say. It's not right, belong or equivalent to nanotechnology. So I would say currently I did not see much impact directly from nanotechnology to food, unless it's indirectly through the gene technology. Yes?
You made mention of side effects of nanotechnology in terms of health analytics. I mean, given the fact that you said using cosmetics in terms of side effects, can you specifically mention what type of side effects one can is using those cosmetics that you mentioned?
I have to say that I'm not sure I have an exact side effect. Otherwise, I may be sued by the cosmetic vendor because they really claim that the nanotechnology benefits their cosmetics. But I would say that physically, okay, physics, the nanoparticles attached to your face is hard to get rid of. Okay? So if the amount or the density is large enough, it will block your face. Because it cannot be peeled off, and then it's continuously accumulate. So someday, somehow, it will accumulate to a large amount of layer that will stick to your face and block your face, so that your skin cannot breathe. That's physically speaking. But then cosmetics vendors will challenge me. I can imagine or fabricate, produce another, like say, facial cover. And then it peels off nanoparticles easily. Then I would say, okay, you solve it. And then you make money twice. Okay, so sometimes people initiate one technology and to solve the problem of a previous technology, and they make money twice. And then if you want to make money 3 times, then you combine those 2 things together. You said, I can have a cosmetics with nanoparticles, but when you finish it, I can peel it off easily. Then you can make money 3 times. Yes?
My question is related to application. So if by using nanotechnology, you can rearrange atoms, right?
Yes.
So in that case, the carbide and diamond, the atoms, like both are using carbon atoms, right?
Yes.
So the one is the structure is different. So when we rearranging carbide atoms, can we make diamonds?
Yeah, we can make diamond. People are using CVD to make diamond, no problem. Okay, the chemical vapor deposition. So use the carbon molecules, you develop, you accumulate, form diamond. You're right. But then,
So in the future, there is no value for diamond.
cost. Right, you see, Professor Xie already mentioned the point. How much you spend to have those carbon molecules fly in the air and then accumulate, shape up the same type of diamond that you want to get. And remember, those diamonds are kind of amorphous and ugly, and even it is sharp and tough. So it is for industry. Okay, you know there is an industrial knife with a head as a diamond, so you can cut things easily. Those diamonds, most of them currently come from the diamond with a chemical vapor deposition. But the cost of fabricating such large diamond, unaffordable. So rather you will put the same amount of money to dig a hole and to get a diamond out of the ground.
So other thing you mentioned about the Lotus Effect, right?
Yes.
So currently we are using Lotus Effect for solar panel.
Yes.
So why don't we use it for example, like when we ride a motorbike, we have a lot of air pollution on our face. So can we create some face mask using the Lotus Effect which can help the dirty things?
The same answer, cost. You don't want to buy a helmet that costs you $100 US, right?
But whatever the technology in the beginning, the cost might be expensive, but it doesn't mean that the cost will be the peak every time.
Exactly. So if you can develop like a mass production way that to fabricate those nanostructures on the face stroke of your helmet, then you can make money. That's true. That a lot of resources devoted, the cost may goes down. But as time goes by, yes. But currently, well, and there are alternatives, I would say. That's another thing. That you can have other coatings rather than create nanostructures. Then you can have a similar result, even not at the same level, but maybe better. Then that's already okay. Because the solar panel already just make you money. So you don't want to waste too much to make it clean. So make it waterproof and clean enough, that's fine. So if coating can work, okay.
My final question, can we make miniature nuclear weapons by using nanotechnology?
Well, good question. Then you have to think about the effect, the area. Tiny weapons.
Yeah, like tiny weapons, we can use the robots.
Yeah.
So millions of nanorobots can fly and then it become a nuclear effect. Of
Yeah.
course, if you consider one tiny miniature nuclear weapon, maybe not much effect, but we can use it with nanorobots and millions of nanorobots because we can see it. So it might be a good weapon in the future, right?
Yes, you are right. Yes. Unite makes strength, I would say. Right? So basically, 这个叫 in Chinese we have a saying, 蚍蜉撼大树. The tiny bugs, if you accumulate enough amount on a tree, you can shake the tree. Yeah. Okay. Any other question? Yeah, I guess it's about time. And thanks for your attention again, and see you some on campus.